Okay, so thank you very much for the invitation and for the opportunity to give this set of lectures here. So let me say a little bit what I'll want to do. So I mean, the last few years there have been a number of applications of derived categories, stability conditions, and wall crossing towards questions of much more classical flavor in algebraic geometry. In particular, towards birational geometry of moduli spaces. But I mean, actually what I'll focus more on is something else, which is not a new result, but I feel it illustrates the methods really well and is very interesting by itself. Namely, I'll give you a reproof of the classical Bell-Noether theorem in the course of these lectures, or reproof the Bell-Noether theorem for devices on curves. And because somehow, once I've explained this, it will also be easy, somehow very natural to explain some of these applications to birational geometry of moduli spaces. Right, and actually my goal, for what I'll do today is I'll just give you the definition and construction of stability conditions. But right while I'm doing this, I'll try to convince you that, I mean, the whole time this is really closely related to algebraic geometry. So, I mean, in a way, the whole time the derived category machinery that one needs is fairly minimal. I mean, it's really right, there are no DG categories, no A infinity structures, no higher categories. It's really, in a very elementary, most elementary approach towards derived categories in a sense. And when one does these applications, one is really working a lot just with algebraic geometry questions. And for today, I'll try to convince you that this already happens just when you try to construct them for surfaces. Right, and so, but let me start with the definition. So for now, right, so I'll definitions. So the setting here is that I'll start with a projective variety over K. Some field K that can be arbitrary at this point, and then by d of x, I'll denote the bounded derived category of coherent sheaves on X. So complexes of coherent sheaves up to quasi-isomorphisms. And I'll also fix something like a Chern character, or it could be a quotient of the Chern character. So by which I just mean, so I take a map from the K group of X, or the K group of this category, or K group of coherent sheaves to some finite rank lattice. So it could be something like a Mukai vector. Right, and of course, I could take the image of Chern inside the cohomology of X, of the usual Chern character. And so I'll just now give you the definition of stability conditions, and then basically relate all the properties back to algebraic geometry at the hand of constructing these for surfaces in the second half of the talk. Right, so let me start with the definition. So the stability condition on X so this is a pair ZA of some categorical data. So A inside D of X is an abelian subcategory So more precisely, I should say the heart of a bounded T structure. And Z is a group homomorphism from lambda to complex numbers. So that's called the central charge. Okay, so this is the entire data, and they have to satisfy the following three conditions. Satisfying 1 to 3. And so the first one is actually, in a sense, the most important one. So when I have an object in this abelian subcategory, then I can look at Z of E, so I'll always use the shorthand notation for Z of Chern of E. This is now a complex number, and I want this complex number to land in this semi-closed upper half plane. Right, so I take the upper half plane union the negative real line. And the way to think about this really is that I have two functions on A that are additive on short exact sequences with some positivity properties. Right? So I can think of the imaginary part of Z of E as a rank function, a non-negative function additive on short exact sequences. And the negative real part I can think of as a degree function. And what's the positivity property of the degree? Well, if the rank is equal to 0, then the degree is positive. Right, and so from this I get the notion of slope. In this abelian category, I just take the quotient of what I call the degree and what I call the rank. And I mean, then I have a usual notion of slope stability, right? So E and A, slope semi-stable. If for all, whenever I have a sub-object, and here I have to specify with respect to the structure of an abelian category on A, that automatically implies that the slope is bounded by the slope of E. Okay, and then the second condition is just that with respect to this notion of slope and slope stability, I have Hadamard-Simon filtrations in A. Exist, right, for this notion of slope stability in A. So any object has a filtration by semi-stable quotients where the slopes of the filtration factors are strictly decreasing. And let me also say the last one. So the last one is easy to sweep a little bit under the rug, but it's actually also, it's both important for the deformation property of stability conditions, and it turns out also to be related, important for these relations to algebraic geometry property. This is the support property, although I won't say so much about this in the course of this lecture, but I still want to mention it now and then. It just says that there exists a quadratic form from lambda to R such that two properties hold. So Q restricted to the kernel of Z is negative definite, and if E is in A is semi-stable, then Q of Chern of E is greater or equal to 0. So I mean, somehow what this property does geometrically, it somehow separates the kernel of the, so say this is the kernel of the inside lambda times r, then somehow it builds a cone around here, and all the stable objects are away from this cone. Right, so here q is less than 0, and here q is positive. Okay, any questions so far? And of course, the example where I don't have to do anything, of course, is the case of curves. So if x is a projective curve, then I can take just A to be coherent sheaves on x, and z of e basically by reverting these two as the relation between the central charge and rank and degree. So z of e is just minus the degree of e plus I times the rank of e. And then slope-stable objects are just ordinary slope-stable bundles on the curve, and so on. Okay, now I'll construct you these for surfaces. And so, I mean, all this that looks fairly abstract, and for now, this will become fairly concrete. And the construction of stability condition on surfaces. And so I have to change my setting slightly here now. So I have to assume that now x is a smooth projective surface. Over k, and I also have to assume that the characteristic of k is equal to 0. So I mean, to my knowledge, it's an open problem whether stability conditions on surface and characteristic P exist, actually, in general. Okay.
In the curve case, what is the quadratic form?
So you can take any positive definite form, right? Because the kernel is 0. Right, so the second part of the condition is vacuous. Wait, which order did I write it? So right, so the first condition is vacuous. So I can just take any positive definite form on it. Okay, and so I also take a polarization. And I do take lambda to be the image of the Chern character inside the cohomology of x. And I mean, the first observation is that I can't even achieve 1 if I were to try to use coherent sheaves. So I cannot achieve just this property 1 with A equal coherent sheaves. So there are no two linear functionals on the K group that have these two positivity properties. And I mean, I won't prove it here, but it's easy to prove. Just write down the central charge of line bundles and of line bundles on curves. And so instead, what one does is the following ansatz. So instead of starting with the category, we start with the central charge, and then try to adjust our category to match the central charge. Right, so I take minus Chern 2 of E plus IH Chern 1 of E plus H squared over 2 churn 0 of E. Right, so I have churn 2 in this direction, h churn 1 in this direction, and h squared over 2 churn 0 in this direction. So how can I motivate this? I mean, just using these two would give me something like slope stability, right, with respect to the polarization h. But I also have to use churn 2 somehow, and then I'm just putting churn 2 in an extra direction further over here. The precise direction actually doesn't matter too much. And now I'll try to construct an abelian category matching this central charge. And I mean, this will be done in 3 steps. And so for this first step, I'll just use slope stability for coherent sheaves. Right, so then I use the usual slope. So it's plus infinity if churn 0 of E is 0, and otherwise I let it be this quotient. And then, of course, I have a notion of the usual notion of mu h stability, and Hadron-Rosen infiltrations exist. And there's just one more thing that I want to add here, namely, what is the? I mean, this is of course not a stability condition in the sense I defined it. But I mean, if you want to cook up a central charge out of this, you'll notice that skyscraper sheaves of points will always get sent to 0, which was not allowed in my condition 1. But it's still something related, and you also have actually in this situation you have an equivalent of the support property 3. And what is this? This is precisely the classical Bogomolov-Giesecke inequality. So if E is mu h stable or semi-stable, and I should say torsion free here, then the discriminant of E, which I'll write as churn 1 of E squared minus 2 churn 0 of E churn 2 of E, this is greater or equal to 0. Right, so it's precisely a quadratic form that's non-negative on semi-stable classes. It doesn't quite satisfy this one here. It's only semi-definite if you try to make the analogy more precise. Okay, and now somehow comes the crucial step of the whole construction. So this is really, in a sense, this is as much derived categories technology as we'll need throughout the course of the lectures. So let me first define 2 subcategories of coherent sheaves that somehow, I mean, implicitly they already appeared in the previous talk. So here these are coherent sheaves such that all the Hadron-Rosen infiltration factors of E have positive slope. Right, or I could have said that the mu min is positive, or let me also write it just to introduce different notation. I can also think of it as the extension closure of semi-stable objects with positive slope. So here, and then I do exactly the same with less than or equal to 0. So I can, all the objects, all of whose Harder-Simon filtration factors have non-negative slope, or the extension closure of semi-stable objects with non-negative slope. And now the crucial construction is the following. Let co h comma 0 of x, I'll define this as the extension closure of coherent sheaves, semi-stable coherent sheaves with positive slope. And co h less than or equal to 0 of x shifted by 1 in the derived category. And then I take the extension closure inside the derived category. Okay, so in other words, I take complexes who are supported in just degree 0, and where this degree 0 part is in here. I take complexes where I have only something of non-positive slope sitting in degree -1, and then I take the extension closure of this in the derived category. So let me make this more concrete. This is really equivalent to the set of objects is exactly given by two-term complexes. So just a map between two coherent sheaves, where the kernel of D is in co less than or equal to 0 of x, and the co-kernel of D is in co h bigger than 0 of x. Right, and of course, I mean, the only thing that's hidden a little bit here that it's not completely obvious is what the demorphism between two such objects are, because I have inverted these quasi-isomorphisms right here. Of course, there's still some modular quasi-isomorphisms here. But still, at least the objects are fairly explicit. And so this is the claim of the proposition that this is the heart of a bounded T structure. But really, the thing that really matters to us, that's actually completely sufficient for everything I'm going to say, is that in particular, an abelian category. Right, and so when I say it's an abelian category, I should tell you what are the short exact sequences. The short exact sequences are just triangles in D of x where all the three objects happen to be in the subcategory, and so on. So an injection is a morphism here where the cone is also in the category, or surjection where the cone is in the category up to a shift, and so on.
What do you mean by bounded T structures?
I didn't want to define it in the course of this lecture. So, but basically, bounded T structures axiomize the properties that if you take just coherent sheaf of X as a subcategory in the derived category of X, you can look at the properties it has. And the two properties are, filtration by cohomology of all objects and no negative X. And then if you axiomize these two, then you get the definition of a heart of a bounded T structure.
So is with respect the bounded means it's with respect to coherent sheaves?
It's with respect, in this context, bounded is a bit. Right, so if you take the unbounded derived category of coherent sheaves, then you don't have a bounded T structure. Then coherent sheaves are not a bounded T structures because you don't have bounded filtration by cohomology. Right, so the bounded here is encoded in the fact that you have a finite filtration by cohomology. Okay, so a few remarks. So. The proof needs a general criterion that is already, has been known for a long time. Hubble right and smaller, I think sometimes in the mid-19s, plus really elementary facts about stability, right? So plus Hadron-Weisselmann infiltrations. Plus the fact that you have no morphism from one of the objects here in co bigger than 0 of x to less than or equal to 0 of x.
What is HRS?
Hubble, Wright, and Smaller, 3 authors. Hubble, Wright, and Smaller. Right, so the statement, the statement is that these two subcategories form a torsion pair. Okay, but I also want to make this abelian category a little bit more concrete. Right, so say you have an object in a coherent sheaves in this subcategory of generated by semi-stables of positive slope. Right, and this, of course, in particular, an object of this co h, 0 of x. So this is an abelian subcategory. So abelian category. So I should be able to tell you what are the sub-objects. Then right. So then inclusions, and here I mean with respect to co h, 0. This is given precisely by the following. So, the first statement is that this A has to be in, the sub-object is automatically also in the subcategory. So this just follows by looking at the long exact sequence in cohomology. And what is the morphism? This is any morphism such that the kernel of f is in co h less than or equal to 0 of x. Right, and so and so of course looking at things like that, it's really close to vector bundle techniques of the 80s. So if you don't like this kind of category, you should have complained in the 80s when people started using vector bundle techniques. And this, as I said, this whole setup will become more powerful once I introduce stability conditions. But already this category explains a little bit that we have some new methods. And what I mean by this is the following. And so co h, 0 of x already gives new methods. So what I mean by this is, say, we want to prove some cohomology vanishing. And let's say we can interpret this by some, I don't know, tensor with line bundles or Serre duality or whatever. Say we can interpret this as some x1 class between B and A, where B is in this category and A is in. Then now, this becomes a morphism, of course, from B to A shifted by 1. And so gamma in this H1 of x comma m becomes a morphism in an abelian category. Right, and of course there you have more methods. You can look at the image, you can look at the kernel, you can try to use stability and so on. Right? I mean, in a way, right? If you're a young, enthusiastic algebraic geometry graduate student and you learn derived categories, you think, oh, this is great. All that algebraic geometry is cohomology vanishing statements, and cohomology classes become morphisms in the derived category. And so, I mean, this must be extremely useful. And then 2 years later, you become desperate because the derived categories doesn't give you anything. And in a way, I mean, what stability conditions do a little bit is to make this initially naive hope effective. Right? So you can really study cohomology vanishing using these methods by understanding cohomology classes not as arbitrary morphisms in a triangulated category, which are hard to control, but as morphisms or maybe extension classes in an abelian category. And then, of course, stability condition itself will give more structure on this abelian category, so it'll become even more useful. Okay, and then I should say one can generalize all of the above. But it's really just a little bit of a shift. It doesn't add so much content of the above. Namely, one chooses what's called the B field, which is just a divisor class. An algebraic class in H11, and then I just replace the Chern character by the twisted Chern character. Chern of by Chern B, by which I mean just e to the minus b times the Chern character. And then mu h gets replaced by mu hb. And this, so I get a more general category co h, 0 of x gets replaced by co h, b of x. Okay, and step 3. And oh, I should also say what z becomes. So z becomes z h, b. And let me write down the formula here. So this is minus Chern 2b of e plus I h Chern 1b of e plus h squared over 2 Chern 0 of e. Okay, and then step 3 says, well, actually we are done. So sigma h comma b. So the pair zh comma b co h comma bx. This is a stability condition. Okay, let me again add some remarks right away. So this is one reason that the stability condition is again not so far away from geometry. And the first observation is that skyscraper sheaves of points are always stable for this. And this actually follows completely immediately from this one. I mean, they don't even have sub-objects in this category. And so moreover, if you have E slope stable, maybe let me say, let me rewrite this a little bit. So let's say I have h dot churn 1 of E positive, also after this twist. So I can always arrange for this by changing B. Right, so then if E is Giesecke stable, which just means slope stable or slope semi-stable plus a small extra condition, then it is sigma h comma b stable for h sufficiently big. If I run to infinity along a line in the ample cone, then it will become Giesecke stable. And interestingly enough, also the converse holds. And again, I mean, I won't prove this here, but it's actually not that hard. Again, everything you need to use are these vector bundle techniques. So you know, if you have such an coherent sheaf, and let's say we already know, right, let's say it's Giesecke stable. So in particular, we know it's in the subcategory. It's in this category. We know what sub-objects look like. And I mean, of course, as you can see from the center chart, I mean, for h very big, the slope of E is dominated by the ordinary slope, and the churn 2 is only just a tiebreaker. Right? So every object that has smaller ordinary slope will eventually have smaller slope with respect to CHB. And so all you need to do is to somehow make this effective, prove some finiteness statement, and for that you use Bogomolov-Giesecke. So somehow Bogomolov-Giesecke allows you to basically put bounds on the churn classes of the possible subobjects here. Okay, and let me also let me say a little bit about the proof of this proposition. So maybe let me do this on the sideboard, so I keep so I have the definitions back up. So I won't give the full proof. Let me say something. Let me do proof of part 1. So this positivity. So if we have E in co-xb of x, then of course C hb of E. This is C hb of h0 of E minus C hb of h minus 1 of E. Right, so this is in co greater b, and this is in co less than or equal to b hx. And basically by construction, it's immediate that the imaginary part of the is non-negative. Right? In fact, here, if you have some torsion-free part, and its Hadron-Simon filtration factor have really strictly positive slope, and in particular positive churn 1. And this also works, or more precisely, I should have said after this twist. So here, h dot churn 1 of B for these objects is automatically positive unless they are zero-dimensional torsion sheaves. And these are automatically non-negative, right? So we have automatically this inequality with equality if and only if, so H0 of E is a finite length sheaf, so a zero-dimensional torsion sheaf. And I mean, how can H minus 1 of E, which is torsion-free and has a Hadron-Sim infiltration, not have strictly positive slope. Well, this has to be slope semi-stable with slope of exactly equal to 0. And in this case, I mean, Bogomolov-Giesinger gives that Chern 2 of B. So if you use this quadratic form, twist it by B, and you also have to use Hodge inequality, Hodge index theorem once, then you get the Chern 2B of H minus 1 of E is less than or equal to 0. And on the other hand, if you look at the real part, the real part of Z of E, that's minus Chern 2B of H0 of E. But since this is a finite length sheaf, this is just a length, or just the ordinary Chern 2. This is then minus H squared over 2 Chern 0 of H minus 1 of E. And then plus Chern 2B of H minus 1 of E. Right, so this is less than or equal to 0. This is less than or equal to 0, and this is less than or equal to 0. And unless all of these objects are 0, one of them will be strictly. One of these two inequalities will be strict. Right, so in other words, the construction of stability condition relies directly on the Bogomolov-Giesinger inequality. Let me also say one word about 3. So again, you deduce this from the Bogomolov-Giesinger inequality. So roughly speaking, the idea is, I mean, we now really try to think of this stability condition as a deformation of slope stability, right? So in the formula above, you can think of adding a factor alpha times Chern 2B of E, right? So something like Z alpha HB of E is something like minus alpha times Chern 2B of E. And we let alpha start at, and all the other parts normal. We let alpha start at 0. There we have slope stability and increase it towards 1. And some of the ideas that Bogomolov-Giesinger, and right, and we run this, we deform the central charge and look at what happens to our semi-stable objects. And there will be some wall crossing. Some objects will become unstable. Some new ones will become stable. But the basic idea is that such a quadratic inequality does not get destroyed. Does not get destroyed by wall crossing. Right? So it's deduced from Bogomolov-Giesinger inequality. And really the only thing you have to do is, I mean, the quadratic form would really be the discriminant. The only issue is that the Bogomolov-Giesinger inequality actually doesn't hold for torsion sheaves. So for slope-stable torsion sheaves, which are also Giesinger stable in the limit. And I mean, if you have devices of negative square, this doesn't work. So you have to add some term of the form h dot Chern 1 squared with some factor here. Okay, so I'll stop here for today. So on tomorrow, I'll start using these for K3 surfaces and reprove you the, Lazarsfeld result for Bernoulli for curves lying on K3 surfaces. Just using this category and some simple wall crossing arguments. Okay, thank you.